Okay, in this video, we're going to talk about the paired sample t-test. So if we go back to our specific design, remember we're starting with populations of interest, getting to samples, and from the sample, we have different conditions, okay? But the difference in this particular session is that the population of interest, right, we get a sample of the population, and we had this 128 group of people. In the independent samples t-test, we then randomly assigned the folks to 64 in the aerobic exercise group and 64 in the control group. But in a paired sample t-test, all 128 people both get aerobic exercise, then they let some time pass, and then they have all 128 people do the control experience to determine if treating the person as their own control yields statistically significant differences in the means and standard deviations of the sample amongst themselves. And so a person from the population gets selected to participate in the study. They represent this 128 people that is largely inferential to the population of interest. And then the 128 people are randomly going to participate in order, either the control group first and then come back later to do aerobic exercise, or start with aerobic exercise and then perform the control group session later on. But the bottom line is when you enter this kind of a study, you have to experience both experiments. You have to experience the aerobic exercise and have your blood pressure checked, and you have to experience the control, seated control session and have your blood pressure checked. The key here is that the same group of people are experiencing all possible conditions, whereas in the independent samples t-test, you only experienced one. So moving forward with our power analysis, right, we're still sticking with the t-test family. The statistical test that we want in this case is going to be the means and the difference between two dependent means or matched pairs. They're dependent because the same people are being assessed on more than one time point or in more than one condition. So when we look at the power analysis, we keep everything else the same. A priori, how many people do I need? Two-tailed test, alpha 0.05, power 80%. We need 34 people to reach 80% threshold. So I would not conduct this experiment unless I at least had 34 people. I kept the numbers at 128 because it's a similar type of concept from the independent samples t-test. And so you need at least 34 people in order to run this kind of an experiment. So let's look at another example, right? So does exercise lower systolic blood pressure? So in this particular case, right, our power analysis told us that we need 34 people. And 34 people need to go through both the aerobic exercise condition and then have their blood pressure checked afterwards. And then the same people have to take a little bit of a break or come back another day and go through the control experiment and have their blood pressure checked after 40 minutes. So the key here is that the condition, not the group, the condition that people experience is either 40 minutes of an aerobic exercise session first and then a seated control session, or a control session first and then aerobic exercise later. You can randomly assign that. That's one of the beautiful things about research is we have degrees and different ways in which we can randomize. And your dependent variable in this particular case is still going to remain systolic blood pressure after 40 minutes. So why is a paired sample t-test or a dependent samples t-test or a matched sample t-test the right tool to use in this context? And the reason is because only two means or two levels exist in my independent variable. So my categorical variable is still treatment. I either have to first go through aerobic exercise and then control, or I first have to go through control and then aerobic exercise. But then I'm going to switch and I have to do the other one as well. But in either case, I have a mean and I have a standard deviation of the same group of people going through the experimental group, the aerobic exercise, and then I have a mean and standard deviation of the same people going through the control piece. Okay, so the key here is that because participants are repeatedly tested for their blood pressure under those two conditions, that is why this paired sample t-test is the appropriate tool for this kind of design. And then lastly, our dependent variable of interest, our outcome variable of interest, has to remain interval or ratio level of measurement. So when we look at our hypothesis testing, what would our substantive hypothesis look like? Let's say that post-measurement blood pressure will be lower after 40 minutes of aerobic exercise compared to the 40-minute seated control condition, right? The statistical hypothesis is therefore going to say there's going to be no significant mean difference between the post 40-minute systolic blood pressure after comparing a control session compared to an aerobic exercise session. And the alternate would say that a statistical mean difference will exist when blood pressure is measured 40 minutes later between the 40-minute control experiment and the 40-minute aerobic exercise experiment. Symbolically, you can see that this is also represented well, where HO is our null hypothesis, and you can see that the mean of the exercise group systolic blood pressure will be the same or not different from the mean of the control. The first alternative will show that the mean for the exercise group will be larger compared to the mean for the control. And then the second alternative will show that the mean for the exercise is less than the mean for the control. So when we talk about basic assumptions, we're talking about conditions that need to be met in order for the data to show what it intends to show. So what are our basic assumptions for a paired sample t-test? The key is that we first have to have what's known as the difference between the conditions has to be normally distributed. And this is a very specific, unique thing about paired sample t-tests compared to the other kinds of t-tests we've talked about in this lecture. So in the independent groups t-test, we talked about how the normal distribution needed to be true for both the experimental group and the control group. But because they're matched or they're related or dependent, we first do it a little bit differently. We have to find the difference between the experimental group and the control group. And then you're going to get something known as a difference score or a D-score. We want to know in a paired sample t-test if the D for difference, if that normal distribution is normally distributed. So we're not interested in the normal distribution of condition 1 and condition 2. No, we first have to determine something that's known as D for difference, and then we determine if the normal distribution of the difference, or D, is effectively meeting those normal distribution assumptions: bell-shaped, asymptotic, continuous, and symmetric. The second of the three assumptions, therefore, is that the dependent variable of interest, in this case, 40-minute post-exercise and post-control systolic blood pressure, if it is a continuous variable, at least ratio level of measurement, and that is also true. And then lastly, we assume that the scores that are collected for the means and the standard deviations are matched, dependent, or related to each other. And they should be, because remember, the same group of people are being assessed more than one time. Okay, so how do we perform the math on this, right? So the beautiful thing is, because we are testing the same group of people, we do not have to worry about generating something known as pooled variance. And so what we're interested in is the numerator, systematic variance, that represents D bar. So D bar, remember, D is the difference between each person's experimental blood pressure and that same person's control blood pressure. So the difference represents that person's D, and you take the average of all of the Ds in the sample, which represents that numerator, okay? For the denominator, we're looking at the standard deviation of the matched pairs divided by the square root of the sample size, okay? So it's a little bit more straightforward in matched pairs, and the beautiful thing about using matched pairs or dependent samples or treating a person as their own control is you don't have to worry about, are these people different, right? Because it's the same person who's going through different conditions. And so if they respond differently, you can be pretty confident that the reason that they're responding differently is because of the intervention, okay? Lastly, let's look at the effect size. So similar to generating the effect size for other types of data, such as the independent samples or the independent groups t-test, right? We're still going to take the mean for the experimental condition minus the mean for the control condition, and then we're going to divide it by the pooled standard deviation. So that's similar in terms of how we calculate the Cohen's d statistic for a paired or matched sample t-test. When we go to our t-table, once again, we're using a two-tailed test and a 0.05 alpha level, and we have, in this case, 128, or I believe I might have changed it to 34. So we'll do 34 in this case, since that's what our power analysis showed. So once again, 34 is closer to 30 than it is to 40. So we'll stick with the 30 row, find the 0.05 value, 2.042. And so that represents our T critical value that we compare the calculated T statistic to. Okay. And so if the T statistic calculated is significantly different or higher on an absolute basis, a larger number than the T critical value, then that means there is a statistically significant difference between people who experience aerobic exercise and what their blood pressure looks like 40 minutes later, and a seated control session where they don't engage in aerobic exercise and their blood pressure is checked 40 minutes later. So any difference that we may see, it's attributed to the aerobic exercise. So how would we write up the statement of the finding in this case? We might write it up in APA style as such. A dependent samples t-test was performed to compare the mean resting blood pressure after 40 minutes of aerobic exercise and a 40-minute seated control session. The post-exercise systolic blood pressure, I didn't put means in this particular case, but it's just a template that you can use for your assignment, was lower than the post-control systolic blood pressure. And you calculate the p-value, the t-statistic, etc., and you acknowledge it was a two-tailed test. The difference in however much the absolute value was in millimeters of mercury indicated a large effect, and the 95% confidence interval around the difference between the groups was relatively precise, right? So these are examples of APA 7th edition style of how you would write up your findings. And the conclusion statement might be that 40 minutes of aerobic exercise sessions are expected to acutely lower your blood pressure compared to a seated control session. And so the implication would be that if someone's struggling with blood pressure, or even if they're on the fringe of hypertension, doing exercise for 40 minutes can lower your blood pressure, and that keeps the doctor away and keeps the medications away, which is something that's really good, something I'm very passionate about as a researcher. So now that we've sort of talked a little bit about the parametric statistics, a common question that we would get in the last video is what happens if the basic assumptions are violated for the t-test? Do we just have to throw our data out? We'll have to find out in the next video, but the key is we'll use non-parametric procedures. So we'll see you there.